So I wanted to thank, first of all, Manny for inviting me for this talk. Hi, so my name is Sattath. I'm going to talk about quantum mining. And based on these two papers, the archive number is here, and the second one is with Bolton Bailey. So I assume that you know very well how Bitcoin works. I will explain a few minor details, but kind of my assumption is that you do understand Bitcoin in detail, and that you don't need to understand anything about quantum computing. Unfortunately, you won't leave knowing more about quantum computing, just some of the properties of a specific quantum algorithm, and that's it, right? I won't explain how these algorithms work at all. So the outline is, we'll start with Grover's algorithm. This is a very well-known quantum algorithm, which is useful for finding a needle in a haystack, and it does so quadratically faster than a classical computer. Sorry. Again, we'll discuss the properties, not the algorithm itself. Then we'll move on to part two. Part two is kind of the long-term setting, where we assume that all the miners switch to quantum mining. Okay, this algorithm that I mentioned before is very useful for mining, so it's better for miners to use this quantum algorithm, and therefore, in the long-term future, I expect miners to use quantum hardware. And one may think that it doesn't matter much, but it is. Like, you already know that Bitcoin switched from, say, CPUs to FPGAs and to GPUs and to GPUs, then ASICs and CPUs, FPGAs. For some reason I can't tell it in the right order, but never mind. And ASICs was the final one, and you might think, yeah, why is it any different? And it is different, and we'll see why. And to avoid a high stale rate, we'll need to change the tie-breaking rule. And I'll explain why this is so, etc. Otherwise, there'll be too many forks in the chain. And in part 3, we'll talk kind of on the intermediate regime, where the first quantum miner joins the network. And we'll show that a quantum miner with a fairly low hashing rate of 1% can attack the network, and in particular double spend. Okay, can get full control of the network. So even though he has 1% of the hashing power, he will be able to generate the majority of the blocks in the chain. Okay, and in particular double spend. The attack, most crucially, the attack isn't practical. It would take too long. The reason is that in practice, even in the long term, a miner would never have 1% of a single quantum miner would never have 1% of the hashing power. I'll explain why. Okay. So to part 1, we'll talk about Grover's algorithm. So what's the problem that Grover's algorithm solves? Suppose I promise to you that behind one of the curtains, there is a prize. You don't know which. I chose the curtain at random. Okay? You want to find the hidden curtain behind which there is a prize. What can you do classically? Brute force. You try one by one. Suppose you ask me to open the third curtain, you see that it's empty. The fourth, it's empty. And then you're lucky, right? Kind of, I can think, like, you could probably easily convince yourself that there's nothing better than that. Just brute force, asking one after the other. If there are n curtains, you need roughly n attempts to find the prize with high probability. So, okay. So, how is that related to Bitcoin mining? So first of all, this is also called finding a needle in a haystack. And the nonce is essentially the curtain number, right? Every nonce is a curtain number. A valid nonce is the curtain number of the prize, right? The miners are trying to find a nonce such that there is a prize in some sense behind it. There are minor differences. First of all, in Bitcoin, there are many valid nonces for, an attempt. So we'll address this issue when we'll discuss Grover's algorithm when there are a few needles in our haystack, not only one needle. And the way I phrased it to you, that you ask me whether there is a prize or not, right? In practice, in Bitcoin, what do? You compute the hash, right? It's not a protocol between two people, just the miner tries and see whether the hash is, like the nonce is valid or not, right? Okay. And the difficulty in Bitcoin is proportional to n over k, where k is the number of prizes, right? So everything here maps nicely to Bitcoin mining. Okay. So what's Grover's algorithm? Grover's algorithm is an algorithm that finds miraculously, right? Finds the winning like the prize, using square root of n queries rather than n. Again, I won't explain how it does it, but it works. So for concrete example, suppose we have 1,000 curtains. Sorry, 1,000,000 curtains. Classically, you will need to open roughly 1,000,000 curtains so that you'll find the prize. Here, you need 1,000, right? Some other important properties. Grover's algorithm is made of steps, which we call Grover iteration, and you could stop and measure Grover's algorithm whenever you want. If you stopped it after q iterations, the success probability is roughly q squared over n. Okay? So if you plug in q equals square root of n, it's square root of n squared, so this is n over n, this is roughly 1, right? So you could definitely find it using square root of n, but even if you do it using fewer queries, you will get an advantage, right? A nice quadratic advantage. And if you failed, suppose you tried to use Grover's algorithm for a few steps, and your success probability was, say, 1 in 100, and you failed. Then you have to start from scratch. It doesn't help you at all for if you failed, right? This is related to the measurement of like that many mentioned about the cat. It's done. You can't undo this measurement and reuse that state. If you failed, you failed.
Unlike the classical one, where if you
yeah.
look at 10% of the doors, then you only have to look at
the... Yes. It's very different than the classical setting. Exactly.
You must decide in advance how many iterations you must do.
No. I think even I have okay. You can stop it and measure whenever you want. You could decide, I don't know, you did 100 iterations, then for some reason you decide to stop, you can do that and measure.
Okay, all right, but you must, if you want to find the answer, you must decide now I look. You don't reach the conclusion after some iterations?
Yeah, you could just, at any point in time, you could stop and measure, and this will be your success probability.
But you have to measure in order to know if you found.
Yes, you have to measure,
right,
and if you failed, restart.
All right.
Okay? Good. So just to emphasize the previous point, suppose n is huge, and you try classically for many iterations, your probability of success grows linearly, roughly. Right? So this is a graph over here. Quantumly, it goes quadratically, right? So the main message that I want you to remember is that the more time you invest, the higher your advantage is compared to classical competitors in some sense. You, as a quantum miner, wants to run for a very long time, as long as you can get, right? Yeah, that's a good point. That's there could be. Yeah, you're right. But if you manage to mine for longer without someone else kind of
And
outrunning you, the better.
when we are talking about mining, we're talking about mining of a single block or a chain of multiple.
A single
blocks?
block, like yeah, you could do. I'm not sure if I understand the question. It's very similar to what happens classically.
Okay.
Every miner tries to find one block after the other, right?
Okay, so not like I want to find like five
No.
blocks and post
No.
them.
No. All right. Thanks. Okay. What happens if there are K prizes? So whenever we had an expression with N, now it should be turned to N over K. So before the success, the time it took you to find the needle in the haystack was square root of N. Now it's square root of N over K. The same thing for the success probability. Before it was 1 over N times Q squared. Now it's K over N times Q squared. This is how it behaves. This is my cheat sheet, right? Hopefully it's simple to remember.
If there are K prizes, the number of queries required to find the prize, a prize.
A prize.
At least one.
One, yeah. It won't help you to find two. It's a prize.
Oh, you will never find more than one.
If you run multiple times, this is for finding a prize.
Okay.
Okay. One of the advantages of like brute force search is that it's amenable to parallelization, right? That's, I guess, why we have so many miners, right? You could easily divide the work. Each miner just separately tries to find the block and it behaves nicely, right? If you have K miners, you'd simply, the success probability of yours will grow times K what a single miner would do, right? In other words, T classical computers cut the time by a factor of 1 over T, right? Unfortunately, in the quantum setting, it doesn't work with this way. If you have two quantum computers, they find the prize using square root of N over... Okay, before it was square root of N, right? Like this is by a single quantum miner. Now it's square root of N over T. Notice that the denominator is square root of T. Right? So if you have, say, 1 million computers, right? How much time does it take you to find the block? It's not that you cut the time by 1 million, it's by 1,000, right?
Less efficient.
Yeah, less amenable to parallelization. Yeah. Okay. I mentioned that I won't discuss how it actually works and actually just the model of quantum computation at all in the talk. Pretty much every textbook about quantum computing includes Grover's algorithm. This is one of the simplest and nicest actually algorithms to explain. And there's a self-contained YouTube video by 3 Blue 1 Brown. If you haven't seen his videos, go ahead and have a look that explains Grover's algorithm in 30 minutes or so. Everything is self-contained, and he's doing a better job probably than I'll be able to do.
Do you get any advantage of having more qubits than are required, or do you need to get into say 50 qubits and that's what's required? But if you get
So basically, you need. So I think what you're asking is like time-space trade-offs. Am I correct?
If I'm getting more qubits in my computer, can I be faster than
So,
the minimal one?
Yeah. So if in order to run Grover's algorithm, if your like search space is n, like over n bits, you need n qubits. That's about it. So you don't need lots of qubits to run it. The main problem is it would run for a very long time. So you need actually a computer with few qubits, but that would run for ages. Okay. Now, you know what? I will give a remark, like I will comment about that. So currently the computers we have roughly 100 qubits, like an order of 100 qubits. So having, I don't know, 300 qubits, which you would definitely need for something like that, that's actually fairly simple. The main issue is that these qubits are extremely noisy, okay? And their kind of lifetime is about a millisecond. We'll talk later about some numbers, but I think I mentioned already you need the attack would a naive attack would take 800 years. So you have too many orders of magnitude here to kind of to bridge the gap. The current computers run for a millisecond. We need 800 years. So yeah, there's a huge gap. So I guess my point is you don't need so many qubits, and that's actually very close to what we already have. But the main problem is that you need them to be very, durable or clean qubits, and the current ones are do not behave this way.
So but beyond error correction, you're saying that you don't have a way to make it faster if you have double the qubits that you have for... No,
we don't know. We know that there are lower bounds. It won't help you. We even know that. It cannot help you. It cannot help you. Grover's algorithm is optimal.
It's contradictory to what you just said, that if you have T quantum computers, then it does speed it up.
Sure, but he was saying like a single quantum computer just with more qubits.
What's the difference?
It's still one CPU. It's just that it has more memory. Think about it this way.
So this is memory versus CPU
discussion? Yes.
Got it. Okay, thank you.
Yes. Unless I misunderstood. Am I correct in my interpretation? Yeah, okay. I think that this is what he meant.
I think that the main difference is that you can have a state on all of the qubits together.
Wait, but the point is you don't, like, even if you have more qubits, it won't help you to run Grover's algorithm faster. There's no better version. Yeah, I think that was his question, right? If you have even more qubits than 200, yeah, you could, but it won't. There are no, like, Grover algorithm is tight. There's no algorithm that would outperform square root of n.
But you could, if you had k, like, you can then use.
If you had k machines.
No, if you had k, I'm just thinking aloud. If you're not looking for one prize, but
k prizes. Again, it's also optimal for. Okay, let's do it offline, but essentially there are lower bounds for that as well. It has been studied extensively, these types of questions. Okay. So now we're ready for the fully quantum mining setting. Again, this is the long-term setting where all the miners have switched to quantum computers. The upshot is that the Bitcoin network will become less secure once Bitcoin miners use a quantum computer. Essentially, the reasoning is if the miners will use quantum Bitcoin mining, there will be a high stale rate. There will be many forks in the chain unless the rules are changed. With the current state of affairs, there will be many, many forks. And I'll explain why. Okay. At least for now, we know that a high stale rate has known negative implications on Bitcoin security. Specifically, it becomes like double spending attacks require less computational power. Selfish mining becomes profitable with a smaller hash rate and longer confirmation times. These are the known implications in the classical setting, at least. I guess the good news is that we propose a countermeasure by changing the Bitcoin protocol, one tiny part of the Bitcoin protocol, which I'll explain. So just a reminder regarding the current tie-breaking rule. Suppose that a fork occurs. Which tip will an honest miner try to extend? A very short fork, right? A single fork.
The one with the more flow.
But they have the same length.
Randomly?
So first.
The current tie-breaking rule is whatever you saw first. This is the current rule. You could ask why is it, but I won't get into that.
It's not a protocol rule, right? It's just like de facto rule.
It's not called a consensus. I forgot the terminology that Bitcoiners use for that. You could do whatever you want, but this is the honest protocol. This is the default. Sorry, it's not even a soft fork. You're right. Soft protocol. Oh, soft protocol. I don't know how it's called. I think there is a name for that, which I forgot, for the rules that are not enforced. Sorry? But never mind. Like, we all agree about that. The name is not so important. And I'll change that. So you might say even, okay, I'm very happy with it because it's not a part of the protocol according to your terminology. Great. So I'm happy to go to your camp. It's a good camp. Okay, great. Okay. So now, suppose we're in the quantum setting and you've heard of a new block. There are two options. The strategy, which I'll call the peaceful strategy, which is to stop Grover's algorithm and start mining on top of the new block that you've just received. And then there's an aggressive strategy, which is measure the quantum state that you just have. Right? You work for 7 minutes. You've heard now of a new block. What would you do? The alternative is, well, you already worked for 7 minutes. Measure, hope to find a block, right? And if you are lucky, post it, and hopefully the other miner post it very, very fast, and hope that they will join your tip rather than the alternative. Why not? It's kind of a dumb question, right? In some sense. Rational miners will use the aggressive strategy as it is strictly better. There's nothing, you don't lose anything. And you clearly win something, right? If you're fast enough, if you have better connection to the network, you win. So hopefully I convinced you that people will use the aggressive strategy. Now what happens now? Once one miner finds a block, all miners simultaneously also measure. This is a very different phenomenon than what happens classically, right? When you find the block, nothing very interesting happens, right? They switch to a different, to mine on top of your block rather than, but essentially there wasn't anything drastic happening. Here, once one miner finds a block, all the others come and immediately measure. And I hope that you have the intuition that this will cause more forks, right? And I want to emphasize that this happens for, like, even now, there are some forks in the blockchain, right? But this happens for very different reasons, right? Now, forks happen rarely because once, say, a day, two miners have created the block roughly at the same time before they manage to hear about each other's block. Now it happens for a totally different reason, right? And therefore, the behavior would be different, and in particular, the stale rate does not go to zero as propagation time is decreased, right? Even if they're all very, very close to each other, there will be a high stale rate. Okay. Now, to demonstrate it, and I won't get into the math, there's a closed formula for what happens in a very simplified setting in which all miners are symmetric, right? They have exactly the same hardware. I assume that also n approaches infinity, like the numbers of miners is big, and they choose the same number of Grover's iteration to apply, right? And this is like the x-axis here, right? T. And the following is the stale rate in this case. So if, for example, they decide, if everyone decides to mine for 5 minutes, you see that the stale rate would be roughly 20%, right? Unfortunately, I don't have the analysis for the equilibrium strategy. It's kind of even hard to define. I won't get into why. So I don't know exactly what the equilibrium strategy is, but it seems like no matter what it is, it will be high. And luckily, there's a simple countermeasure. Now, this is probably the trickiest slide. It's not so crucial if you don't understand. It's no big deal. I'll try to do it slowly because, again, it's a bit tricky. So what's the intuition behind the proposed the countermeasure? So the intuition is we want miners to use the peaceful strategy. We want to rule out the aggressive strategy. Okay? There is a political message hidden there, right? how can we do that? How can we make sure that the aggressive strategy won't be useful? I want the ones that mined honestly to get the reward, or that other miners will join them, rather than the one that use an aggressive strategy. How can that be achieved? That's the question that we're trying to solve. And what's the intuition? We'll use the timestamp. Okay? I'll explain in what sense. So, remember that the old rule is to follow the tip that was seen first. Right? So, suppose T1 and T2 were the time for the competing blocks, then the honest miners will join the one that minimizes TI. Right? If T1 was received first, or T1 is minimized, they'll join this one. We will change the tie-breaking rule by taking the timestamps into account. Why is that a good idea? So first of all, let's remember that when you receive a block, every block contains the timestamp on which it was mined, right? Now, imagine that I'm an honest miner. I plan to mine after 5 minutes. Suppose now it is 8 p.m. I'm planning to mine for 5 minutes, and I'm honest, and I indeed was lucky, and at 8:05, I mined the block. I know that I'm going to mine at that time, so I'll put a timestamp of 8:05 in my block, right? So I will put the timestamp in at the time of which I will measure. What happens for the aggressive miner? Suppose Ron is very aggressive today, okay? For how long did you plan to mine?
I plan for 5 minutes, but
but I plan to mine for 5 minutes. So suppose you plan for Ron planned to run for 10 minutes. What would be the timestamp in your block? 8:10. We want to prefer my block rather than Ron's block.
I can't change the timestamp while I'm mining.
You cannot do that. For whatever reason, Grover's algorithm does not allow you to do that. You can't change it after the fact, like after you started mining in some sense. So you have to commit to the time that you'll kind of mine. Okay, so the thing that we'll use, the formula that we'll use, is the one that minimizes this expression. It's the absolute value between the timestamp and the time which was received, plus the time that it was received. Now, what happens for my block? I plan to mine for 5 minutes, so my timestamp was 8:05. Suppose I was very slow, and it took me even a minute, okay, until it propagated to the rest of the network. Here it's 8:05, and the difference here is 1. Whereas for Ron, this expression equals 5 minutes. So he gets a huge penalty, right? Of course, in practice, this would be roughly a second. And for the aggressive miners, it would be orders of minutes, right? So we kind of get around aggressive strategies.
But it has a side effect. No,
Take the mic, please.
I mean, if you said that there's an incentive, even without competition, there's an incentive to mine longer, right? Or not to predetermine how long you will mine, and just And so here you have to, by knowing the network conditions, you have to know at this time I'll mine for 10 minutes or.
Yes, you have to decide in advance. And this is I'll get to this question of like what actually the strategy will be.
Something basic I didn't get, because you were saying it's a symmetric situation, so everyone is going to mine for 5 minutes?
No. This was in the previous graph. No, I'm not saying after this proposed quantum measure will be taken, I know that it won't be a symmetric equilibrium, right? It won't be simply that, or a pure symmetric equilibrium. Like it won't be that everybody mines for the same time. I'll talk about equilibrium in a second.
What about lying about a timestamp? Like
Good. Are there any attacks? I don't know of any attacks, but I'm very eager to find ones. I couldn't find an attack on this proposal. But I don't have a security proof either.
The issue is in this case, which it will not work because you need to know when you open the box and see what goes out. So you need to commit to a number beforehand. This is the difference here.
Exactly. This forces that you have to commit in advance for how many iterations. And in the aggressive strategy, you didn't. You just, go ahead. I would say roughly as the same as today, a few seconds to propagate. Not any different than the...
The network today is built that even if the communication is broken, then the good block will still propagate eventually. Like if you have...
But there would be many forks in this case if there's a... So if the same thing in this case. If there are huge delays in the network, the stale rate would go high. Yeah.
Why use the time and not the nonce itself and force all miners to start from zero? So the protocol is that you have to start from zero.
How do you enforce that? Yeah, it doesn't work. Yeah. And the Grover's algorithm, and definitely Grover's algorithm doesn't work this way. They use a superposition. Yeah, I don't know. Let's do it offline. I'm not sure even what. I don't know how to kind of compile your proposal, especially in the quantum setting. Like everything is done in superposition over the nonces. I don't know how to do this sequentially. There is a nonce, it's in superposition. I don't want to get into that, how the quantum algorithm works. Okay? I'll be happy to do this offline.
No, I think it's just my misunderstanding.
Okay. So some open questions here. So the Bitcoin tie-breaking rule needs to be changed in order to avoid a high stale rate. The equilibrium strategy for quantum mining was studied and partially answered in this very, very nice paper by Troy Lee, Mahashire, and Miklos Santa. It's an excellent paper, but now I'm going to, in some sense, bash it. They solve a simple, a toy model in some sense. They solve a simplified model in which this game is a one-shot game, and in which like this miners have one attempt to run Grover's algorithm. If they succeeded, great. If they did not succeed, that's it. Game over. Whereas in reality, it's a repeated game. If a miner tried to measure and failed, he can try again, right? He can continue to run Grover's algorithm once again. Now, this is a very nice paper. Excellent paper. This is already, just a second, this is already 70 pages long of heavy game theory analysis. They did a marvelous work. It's simply that the real question, or the more relevant question, is still wide open about fully understanding the equilibrium strategy in the repeated game.
When you say repeated game here, do you mean that they're re-attacking the same, re-attempting
it's the same block.
Fork?
It's the same block. And suppose a miner tried to find the block. You mined for 10 minutes, and you were unlucky. You weren't successful, right? You mined for 10 minutes and failed. What do now? You'll try again, maybe mining for 5 minutes, maybe mining for an extra 10 minutes. I don't know what you'll do, but you have another attempt to find that particular block.
Yeah, but why should I, instead of joining the peaceful herd?
No, everybody, now we're talking about the peaceful strategy. No one is using an aggressive strategy, but you failed using in the peaceful strategy, right? You mine for 10 minutes. No one else have found a block. What do?
Yeah, you're allowed to mine, right?
But in their game, that's it. Game over. That's what they managed to analyze. And this is extremely difficult already. Okay, so that's kind of my point. They didn't, you're saying, obviously, you try again. But they analyzed the single shot game. Okay, great. Is the proposed solution secure? I don't know. Maybe it introduces new attack vectors. Maybe by itself it's not secure. I'm not so sure about it. This is kind of interesting. And I think I'll stop here. This is for many. You know what? Because he asked me, and I think this is a very good point, and I like this question. We know for problems for high stale rate in the classical setting, which I kind of explain, right? 51% attacks become easier, etc., right? There are a few problems which are known. I'm not sure what happens in the quantum setting. Maybe it's not a big deal. You could argue, so what? There's 20% of forks. How serious is it? I don't know. Okay, so if you have a better understanding, why is that such a bad thing? And I'll be happy to hear about your thoughts.
Why don't the same things apply that you said in the classical case?
Selfish, you're
not selfish mining, but just the fact that you have to outrun the network, you now need to compete with.
I don't know how double spending attacks would look like in the quantum. There are so many aspects here. It's hard to kind of fully figure out. Okay. That's not so clear. Yeah.
Does it create a strange incentive to try to mine 2 blocks in a row? So when you publish them, you publish 2 blocks, and all the others will only publish 1?
Yeah, we don't know about that either, right? Like this is some form of, you're kind of suggesting things like selfish mining, right? So kind of hiding some parts or just even trying it directly to. So there are some aspects which are understood about it. I'll be happy to give I don't remember the name of the paper that analyzes this kind of question. There are some partial answers. I'll say that. Okay. Okay, so the second part, how much time do I have? Okay. The second part is the setting where there's a single quantum miner and many other classical miners, and the single quantum miner has a low hash rate. Think, say, 10% of the hashing power. What exactly do I mean? In this example, like 10%, I mean that if he mines honestly, right? If he just mines for, say, 10% of the hashing power means here that if he mines for, say, 100 minutes, he will find a block with very high probability, right? So he can generate blocks at 10th of the rate of the classical network. Okay? Great. Now, luckily, there was a paper by Kujakara et al. That shows that in a simplified model called the Bitcoin backbone protocol, a small quantum miner cannot double spend, right? And we show that a small quantum miner can generate 100% of the blocks in the longest chain, or in the honest chain. Now you should say, well, this is outrageous, isn't it? Like in the previous slide, I told you, a small quantum miner cannot double spend, and in the next slide, I'm telling you it can double spend. And why isn't there a contradiction here? Because our attack manipulates the Bitcoin difficulty adjustment mechanism, which the simplified model by Kujakara et al. Explicitly ignores. They don't take into account difficulty adjustment. And they were very explicit about this point. Okay? So no contradiction. And I would say that pretty much every newsletter outlet that you will see that talks about quantum computing and discuss Grover's algorithm will say roughly this, that mining isn't a big deal. Usually they won't refer to this paper, but they'll have an intuition that, Bitcoin mining isn't a big deal. And again, this paper, which is an excellent paper, formalized this intuition, but it ignored difficulty adjustment. So we use difficulty adjustment, right? We find a way to kind of manipulate and use the difficulty adjustment mechanism to break the protocol in some sense. So let me just remind you what difficulty adjustments are, etc. So in Bitcoin, there's we want blocks to be created every 10 minutes, an expectation, and a target T is chosen so that the block is valid if the hash of the header of the block is at most T, right? This is how. Now, what happens if miners join the network, right? So maybe there are more or less hashing power. So every epoch, which is 2016 blocks, which is supposed to be every 2 weeks, T is adjusted so that the expected time per block would be 10 minutes. So if, for example, it took the miners to mine it was supposed to take them 2 weeks, but in practice it took them, say, a week. there's too much, like it's too easy, right? We want to make so a block is mined every 5 minutes instead of 10 minutes. We want to make them blocks to appear smaller. So what do? We increase the difficulty by a factor of 2, right? To make it harder. Okay. And the second thing that I need to remind you is like what's the Bitcoin's fork choice rule, right? So some people call it the longest chain rule. I think this is in some sense inaccurate, and the right term should be the most work rule. So if there's a long fork, which tip do you use? Not necessarily one which is the longest. And I'll give an example. So the actual chain, the tip that you use is the one that has the most cumulative proof of work. If you look at the sum of the difficulties, it should the one that has the largest sum. Now, if there are difficulty adjustments in your fork, right? Suppose it's a long-range fork and it kind of tackles like an epoch. It switches between epochs. The different branches might have different difficulties, and then it might not be the same as the longest chain rule. So let's see a concrete example. So here we have a fork, and notice that here there was a difficulty adjustment. And for whatever reason, this block, this part, the difficulty increased by a power of 2, but by 2, and here it remained the same. Okay? So in this part, the cumulative proof of work is 5, right? Whereas in this part, it's 6, even though it's shorter, right? So miners will use this tip, right? The one at the bottom, even though it's shorter. Okay. So the attack intuition is pretty simple once everything is ready. Let's think from the quantum miner's perspective. What happens if you increase the difficulty by a factor of 100? How hard it is for the quantum miner to find the block? Only 10 times harder, right? This is the gist of it. Let's ignore the question, how do we get there? But if the blocks, or if the difficulty increased by a factor of 100, for the quantum miner, it's only 10 times harder to mine such a hard block. For everyone else, they need to find a nonce, which is like with several more zeros, right? With 2 more zeros. Finding a block which starts with 2 more zeros, if you think in decimal at least, it's 100 times harder.
No, but what's not clear to me is what is the difference here between the quantum miners and all the other miners?
Quantum miner uses Grover's algorithm, and Grover's algorithm has a quadratic advantage, right? In some sense, if you use the slides that I talked about before, it's right square root of n, or square root of n over k.
Okay, I guess I'm missing the point, but maybe I don't want to bore anybody. So I understand, but we already stipulated at the beginning of the discussion that this quantum miner has 10% of the hash power. I don't care how it got there.
It's 10% of the hashing power in the original difficulty. In the original difficulty, it has 10%. But now what happens if I increase the difficulty by a factor of 100? For each block, now it's only 10 times harder for the quantum miner.
I understand now.
For the classical miners, it's 100 times. But so we conclude that for the quantum miner, if we increase the difficulty by a factor of 100, it will be only 10 times harder. And how much work is in there? 100 times as much work, right? So that's the intuition of what the quantum attacker or quantum miner will do. The first thing is what will do is increase the difficulty, and then an epoch worth of blocks. And by that time, he's done. He has like more proof of work than the rest of the network. Okay, so that's the intuition. Let's put it in like more concrete terms. the quantum miner, the first step is to increase the difficulty. How does it do that? It creates a block such that the timestamps, it would maybe take him for a long time to mine such a block, but the timestamps are, say, a second apart. Right? They should be 10 minutes apart, but the timestamp that he will put in the block are 1 second apart. Right? What would happen in such a setting? Right? The blocks appear for an outsider as if they occurred too fast. So what do? Increase the difficulty. So in the next epoch, the difficulty will increase. Now the miner will continue to mine in the increased difficulty for 1 epoch. Okay? That's it. End of the attack. So again, I just explain the intuition once again. For the quantum miner, to mine a block of this sort, right? So he increased the difficulty by a factor of 1 over r squared. Here you should think about it. R is 10%, so he increased it by a factor of 100, right? Let's do with the concrete numbers, right? Mining now a block of this sort it contains a proof of work which is worth 100 blocks. How harder it is to mine such a block? Only 10 times harder, right? So now, imagine that he had 10% of the hashing power. Now he kind of multiplied himself by a factor of 10, whereas the rest of the network has 90% of the hashing power. So he's kind of creating blocks which are worth more work than the 90% of the other network, right? By cheating. Okay, you're saying this is an attack. Clearly this is an attack. Okay? And I think I'll stop here.
I think difficulty is broken in the quantum.
Yes. I guess that's a nice way to phrase it. The adjustment, the difficulty adjustment, and the entire mechanism of proof of work, in some sense, is broken. I think I'll agree to that.
There is one little adversary in the world of
yeah, when you're trying to kind of do it simultaneously, having quantum miners and classical miners simultaneously, it's broken. Yeah. How much time? Okay. So why is it? So I think I want to emphasize this slide more than anything. It might seem like a really serious issue, but I argue that it's not as big a deal as it sounds. And why is that? So the attack clearly cannot be done with existing technologies, right? You need to run for a very long time. Current quantum algorithms, current quantum computers run for orders of milliseconds, maybe seconds. No. But suppose we're talking about the long-term case, where suppose quantum algorithm even can run for years. Still, I argue that this isn't a big deal. Why? Suppose that we have really nice computers, quantum computers. They could run for years. What is their CPU rate? How fast are they? How long does it take them, say, to compute a hash? Now, if you've noticed, what's the fastest computer on Earth? How fast does it run? Like a CPU, not in parallel. 10 gigahertz. That's it. The one that you have like in your desktop are like, you can't do more than twice as fast as that, right? Computers cannot run very fast. What do? How did we kind of get around the problem that the gigahertz parallelize? And that's how we get fast things, right? In today's world, right? We still can double, say, the number of cores, etc., or somehow the effectiveness of these computers, but not by increasing the gigahertz. If you want to use parallelization, as I mentioned in the beginning, Grover's algorithm doesn't parallelize so nicely. Okay? So if we plug in the numbers, our estimation, and this is like an optimistic analysis, we in practice, you even need to do more severe like there's more overheads that we didn't, and we stop there. Already, if we plugged in the numbers, where we have a quantum computer running at as fast as the fastest classical computer today, which is 10 gigahertz, the attack would take, unfortunately, 800 years. I would say this is impractical, right? I think we'll all agree with that. So that's why I think it's really, luckily, with it won't work, at least in Bitcoin. So how could we fix the attack in some sense, or what could go wrong in some sense? So first of all, maybe there are more sophisticated attacks which would run for shorter. I don't know. I can't think of any. I guess I should say that the asymptotics here, the time it takes is epoch time, over r squared. Okay? So again, I don't remember the exact number, but I think that's the fastest, like if you plug in 1 gigahertz, it's way less than, say, 1%. So it's 2 weeks. Even if it was 1%, right? It would be like a factor of 1,000. So it's like, say, 10,000. So 10,000 times 2 weeks is a huge number, right? So the fact that there is an E here, for example, is very good for Bitcoin. So if, for example, you have a cryptocurrency in which difficulty adjustments are made every minute, or every 10 blocks rather than 2,000 blocks, it would be much shorter. So that's one way to do that. So attack cryptocurrencies with shorter epoch times, or with a smaller total hash rate. Or maybe I'm wrong here. We kind of assume that you cannot go beyond 10 gigahertz. Maybe you can, say, have a computer with 100 gigahertz, right? It would, again, if you 10 times the... Sorry? No, ASICs are not so fast. It's just that they are parallelized, right? So another route is to parallelize it. So use many quantum computers in parallel, right? And again, the downside is if it took you 800 years, and if you have 800 computers, right? What would be the running time? It won't be a year, right? You get you say a factor of square root of 800. So in order to attack this, if you want to get it to a year, you need roughly 500,000 quantum computers, right? Because it's not so much amenable to parallelization. That's the point that I'm trying to make here, and that's why I told you so much about the parallelization. Okay. Okay, there's one sorry, I'm running out of time. I just want to tell you one last thing. So there's an entire topic which I think most of the cryptocurrency community is not aware of, which is quantum alternative to cryptocurrency, which is called public quantum money and some variants of it. This is extremely interesting. I would say that for example, there was a recent talk by Justin Drake. Maybe some of you have heard of him, and he described it as cryptocurrency endgame if we manage to implement these things. These are very interesting directions to solve some of the main problems in blockchains. And there are 2 papers that I'll urge you to kind of at least read the abstract and examine. And I think in the long term, quantum cryptography has tons to offer. And essentially, you could have something similar to like cryptocurrencies, but without a blockchain. That's the upshot. You don't need to you don't need to solve the consensus problem. There are ways around cryptocurrencies that don't solve consensus. So they are way more efficient. That's it. Sorry?
Someone asked if
No.
was a joke.
That was a joke. Okay. That's it. Thank you.
Thank you.
Yeah, questions.
Sorry, is there a way to change the cryptography to make this linearity property also in the quantum world, so that if you have double the computation power, you have double the chance to...
So there were debates about changing like the proof of work mechanism so that there's no advantage to quantum adversary or quantum miners, I guess. I never saw a solution which I felt comfortable with. I don't think there is, and I think it's fundamental. I don't know of any good solution to this issue. But it's a very nice question. I think it's a natural question, and maybe there are some
because
ideas.
There is Grover algorithm, and basically if it's proof of work, it's brute force, then this quadratic thing is
You need
inherent.
something which is, you definitely need something different, a different idea. Say proof of space or whatever. I can't think. I didn't see something that kind of convinced me that this is a very nice approach. And but there were some papers about it. But honestly, I cannot. Unlike the two papers, for example, that I mentioned, which I highly like. I feel these are really nice contributions for the quantum proof of alternatives for proof of work. I've never seen something which I said, "Oh, wow, this is a really neat idea." Yeah.
Do you think quantum miners will be mass-produced? Or will it be a technology held by a tiny few companies?
I don't think I have any more information than you about these questions. I don't know. I'm not the person to ask. Okay. Thank you so much.